best thing about the Deep Foundations Institute is the collection of engineers, contractors, material and equipment suppliers, and academics. And so bringing everybody together means the stuff that we get done is useful and is immediately applied and is not in some out there academic corner, or it's not promotional to one type versus the other. It's really a true collection of the best of this industry.
Membership of the DFI has many benefits. As I said, there's, for the younger members particularly, there's a wealth of knowledge within the DFI's archives, if you will. The magazines, the journals, the publications. We have this organization called One Mine that we subscribe to, where there are literally thousands of documents on all aspects of deep foundation construction, design, etc. So from that point of view, it's a very, very important resource that comes free with your membership.
Learning about technical advancements, again, seeing what projects people are up to and what solutions other engineering firms have come up with, and then the networking opportunities that we get at the in-person meetings like this conference.
I think the technical committees is just another great way to get involved in DFI. You meet a lot of people in the industry that are very influential and important. They make a lot of decisions that we live by in the industry. So when you participate in a committee like that, you can see firsthand how design and construction is kind of sculpted. So it's a lot of fun, and it's a worthwhile investment.
It's an organization basically that guides not only the principles of what transpires in the Deep Foundation Institute or industry, but also brings everybody together to discuss common problems and provide solutions.
I come because I like to learn about what is going on in the industry. I like to hear from the contractors, especially because being an engineer, sometimes it's good to learn from the contractors what innovations they're coming up with, and obviously to meet with other folks and see what they're working on.
This conference is probably the most important event during the calendar year, so you cannot miss it, because here you can meet a lot of people, contractor, supplier, competitors. So, as I said, it's the most important event in the calendar for foundation business, and it's too important to don't be here, let's say.
We come because we get a lot of exposure to people who use our equipment. A lot of camaraderie. Even with our competitors, we come out and we rub shoulders. Everybody knows everybody. It's just one big happy family.
Well, it depends on whether or not you want to continue learning. If you got a desire to continue to learn, then you need to be at DFI.
The good thing about this conference, you can meet a lot of people over and over, so you can make a very good connection with the industrial people.
Networking's huge. There's so many people here, just from different parts of the country and the state and the world even, and just seeing what processes they're using and their design methods and their equipment, and just really a lot of exposure, and also getting connected with those people for potentially future work, future jobs.
Come join us if you're interested in anything in this industry. This is the place to be. This is it.
Welcome. I'm Mohan Ramanathan from Chennai in India. I welcome all the delegates and the registrants for this DFI India webinar series on steel retaining structures and foundations. This is webinar number 2 in a series of 7 webinars. I once again repeat, I'm the moderator for you for the day. I'm Mohan Ramanathan. I'm chairman of the DFI India 2020 virtual conference that will be held in November. I'm also executive committee member of DFI India and managing director of Advanced Construction Technologies based in Chennai in South India. It's my pleasure to welcome all of you again. And we have almost 800 registrants for this wonderful lecture coming up. It's my pleasure to welcome everybody, and I have a certain housekeepings to be followed. No recording of this webinar. It's prohibited by DFI rules. Certificates of attendance will be issued. It will take 2 weeks. It will be mailed directly to you. Online webinar recording along with the presentation slides will be available to you in approximately 2 weeks from the DFI office. I also wish to tell you that if you need assistance during the program, please use the chat box. You can also make note of the 2 officers who are standing by behind this seminar, behind this talk, and they will help you if you have any technical glitches. I also would like you to take your attention to the handouts. We have 5 handouts which is available for you to download. It has the catalog of the main sponsor, catalog of the other 2 sponsors for this talk. We also have the brochures for all the webinars that are coming up in this webinar series and the annual conference. You can download it, save it, and take action of it. So if you have any questions, you can put it in the Q&A box. Before you do that, please write your name, your organization name, and the question very clearly. The speaker will answer each and every question providing the time permits. The chat box is mainly for communication with the DFI people, mainly for technical glitches. And also you have to, we are going to mute all of you. You're all in the listen only mode, but still if there is any issue, please mute yourself and switch off your video cam. And as I told you again, the handouts are very important, as it is the only follow-up for this that you will have. And please download the handouts. And we'll also be having the links in the chat box for you to register for the conference. Now, I wish to introduce ArcelorMittal Projects India, the main sponsors for this webinar series. On behalf of DFI India and DFI United States, I wish to thank the ArcelorMittal to coming forward to have a main sponsorship for this educational webinar series. We also have 2 more sponsors for this particular talk, which is Kamar Infrastructure from Mumbai and Teamworks Engineering Solutions from Chennai. And these 2 companies are also sponsoring today's talk. We thank both of them. I wish to bring to your attention that DFI India has sponsorship opportunities available for the upcoming webinars. We have 5 more webinars where we have got wonderful speakers on subjects connected with steel foundations and steel sheet piles. And we have got 2 titles already finalized. One is in webinar number 6 on October 7th and webinar number 3 on 26th August. You can see the names at the top. And we have 3 more coming up. And the sponsorship opportunities for manufacturers, suppliers, and contractors are open. You may get in touch with the DFI India office. I'm happy to announce that today we have a record of registrants. We have almost 100+ of registrants for this webinar, and the interest is building up. And you can see that a mix of contractors, consultants, academia, specialists, owners, manufacturers. Really, this is the right platform for anybody to participate or publicize your products or services. DFI is meant for this kind of exposition of the individual's capabilities. Thank you very much. We also have a demographic of the registrants, and we have 31 countries represented. So I don't know actually to say good morning or good evening or good night. So we have from Australia to United States, and the United Kingdom has been added since the last webinar. So we have 31 countries, and it's a record breaking. Thank you one and all for registering for this webinar. The general arrangement and agenda for this webinar will be the speakers. A speaker will be introduced by me, then followed by his presentations and his videos. Then we have the promotional videos of the three sponsors. Q&A session again will be through the Q&A box. Please ensure that you put your name and organization name and a clear question to the speaker. It'll be moderated by Mrs. Amrita. Then we have details of the next conference. We are running up to the virtual conference, DFI's 10th annual conference in November. We'll have some slides on that, and then another few slides about the CFA initiative, which DFI India has taken up, and I will close the webinar successfully. Now it's my pleasure to introduce our speaker of the day. So the topic, as you can see, is the new seismic design methods for steel sheet piles in very high seismic regions. Very relevant topic for the world today, and especially for India. The speaker today is Mr. Amin El Kasimi. He's a project engineer in the design office of ArcelorMittal sheet piling division at Luxembourg in Europe. And he is going through his bio. I find that for his age, he's really achieved a lot. Mr. Kasimi graduated from Mines Nancy in France with a master's degree, master in civil engineering and geotechnical engineering. He joined ArcelorMittal company in 2015 and is now in charge of project design support on a global scale. He's been involved in geotechnical and maritime projects in various applications like quay walls, underground car parks, deep foundations, etc. He is specialized in seismic design with full dynamic methods using finite element method. He has participated in research works related to seismic design of sheet piles in collaboration with well-respected universities. So you have a very young, experienced speaker who is going to talk about very important subject. Thank you, Mr. Amin, for being with us today. It's over to you, Mr. Amin. It's all yours.
Thank you, Mr. Ramanathan, for the introduction. And I would like to thank DFI India for organizing this series of webinars on sheet pile retaining structures. And I would like also to thank all the attendees for today's topic, which is about the new seismic design methods for steel sheet piles in very high seismic regions. So in this webinar, I will first start with an introduction of the topic. Then I will introduce the design methods that are existing today, mainly the pseudostatic one and the fully dynamic one. Then I'll go to some comparative studies that were done in the recent years, comparing the two methods. We'll also talk about important topic, which is performance-based design in this context of seismic design. Also, we'll say a few words about water-related issues like liquefaction and tsunamis, and I'll finish with the ArcelorMittal publications that are still to come this year and very soon on this topic. Next slide, please. So the design state as it is today, we see that quay wall structures are mainly designed using pseudostatic methods, also called conventional methods. These are methods that are mainly based on Mononobe Okabe formula that is well known. What we know today is that this often yields in very non-economical or sometimes even impossible sheet pile solutions in high seismic areas. However, the experience and from recent projects, we see that sheet piles have good performance in seismic areas. So this was the starting point for these works, also research works, to try and understand why the design methods that we have now are not compatible with what we see in reality, and how design methods can be improved. So I'd like to start with this success story here in this port of Mejillones in Chile that was constructed in 2004. This port structure was built after some serious damage to the harbor installation of Antofagasta in the 8.1 magnitude in 1995. After this earthquake, the authorities decided to construct the next port at the northern part in the Mejillones Peninsula, and the breakwater was built using 8 circular cells, 24 meters in diameter and 24 meters in height, and the total length of the breakwater was 200 meters. Also, one key, which is key 3, was built using the HZM sheet pile system with a total wall length of 620 meters. What we saw in the last years is that this port suffered no damage throughout a dozen of very high seismic events. The most famous one was the 7.7 magnitude earthquake in 2007. And what we saw after that is that the port suffered no damages, and we had reports of surrounding concrete-based ports that suffered heavy damages and were left in non-repairable state. So these kinds of return of experience is what encouraged us in this research and try to find the best design methods for sheet piles in seismic areas. So let me start with the design methods that we have today. So mainly 2 design methods, the pseudostatic one and the fully dynamic one. In the pseudostatic method, the loads that are due to the seismic action are actually applied as an equivalent static load. And we are, as I said before, mainly using the Mononobe Okabe seismic earth pressures for this method. The fully dynamic method, however, is based on finite element modeling. We use ground motions as input in our model, and we consider the realistic behavior of the soil using a nonlinear dynamic response. And also what we can see is that FEM in general will give more reliable results compared to pseudostatic, and this we'll see later in the comparative studies as well. So starting with the pseudostatic method now, the principle, so we know that in static conditions, the earth pressure wedge is subject to acceleration of gravity only. In dynamic conditions, in seismic conditions, we have an additional acceleration, horizontal and vertical acceleration due to the earthquake. In our case, we'll be more interested about the horizontal acceleration. And what we do is that the resultant acceleration here, it will be rotated by an angle theta that is related to the seismic acceleration that we have. This method was initially developed by Okabe in 1926, and then later on by Mononobe and Matsuo in 1929. Based on a modification of the Coulomb's theory on earth pressures and what's known today as Mononobe Okabe method. So once we have this rotation of the model, we just derive the earth pressure coefficients, and then we can apply the modified pressure as in the seismic conditions. So you see here that in order to have this theta value or this equivalent rotation, we need some coefficients here, kh and kv. We will be more interested in the horizontal one because that's what impacts more, especially retaining walls. And this is what is called the seismic coefficient. So to determine the seismic coefficient, we need to consider a particular standard. Starting here with the Piank working group 34 recommendations, we have here a graph of some earthquakes and their equivalent seismic coefficient kh. And if we see here just the boundary below 0.2 g acceleration, we have this line here that is describing very well the kh. So that's why here lower than this bound we have just the ratio between the seismic acceleration and the gravity acceleration. If we go beyond 0.2, we have a more complicated formula, but in the recommendations from Piank, we have an average value of 0.6 multiplied by the ratio between the seismic acceleration and the gravity acceleration. So this is basically the formula that we use if we want to do our design based on Piank recommendations. Moving now to Eurocode 8, the European standard, we have a formula that is somehow similar because we have also here the ratio between the seismic acceleration and the gravity acceleration. We also have introduced here a soil factor, that can range from 1 for soil type A's for rock, for example, to even 1.7 or 1.8 for soft soil conditions. But most importantly, we have here a reduction factor. This reduction factor is based on the acceptable displacements of the structure, as you see here in the table. So if we have more displacements acceptable, we can have a higher reduction factor. This factor can be seen, as it was said in the designer's guide to Eurocode 8, it can be seen as a way to consider ductility and adapt the safety factor to permanent displacements. However, if you look closely to the table, you'll see that we're only allowed to have this reduction for gravity walls. If, for example, for sheet pile walls, which would be considered here as anchored walls, we were not allowed to use this reduction, which is a bit contradictory to the fact that we are supposed to consider the ductility of the sheet piles. This was actually criticized by many researchers and will probably be updated and changed in the next update of Eurocode 8 that is ongoing now, and we can further see it in newer European standards like the NTC 2018, which is an Italian standard. Here again, to determine the seismic coefficient, we have the seismic acceleration that would be divided by the acceleration of gravity, but we have two reduction factors, alpha and beta. So if we start with the beta factor, this would be equivalent to 1 divided by R, R being the factor that we just saw from Eurocode. And we can see here for higher displacements, 30 centimeters deformation of the wall, we can have up to 0.38. So that would be 62% reduction of the seismic coefficient. In Eurocode, that's maximum 50%, and it was only limited to gravity walls. So here we see that we are going further, and furthermore, we have also another reduction factor that is depending on the deformability of the soil layers, and that considers the asynchronous state of the waves, seismic waves. And if we consider here, for example, a retaining wall of 40 meters, let's say, the extreme case, and for soil type C, for example, which would correspond to sandy soils, normal sandy soils, we have a reduction factor of 0.3. So we can see that it's a bit different from what we have in Eurocode 8, which starts now dating because it's in the 2000, I think, so almost 20 years now that it's been out, but it's still being used and it's still being the standard that needs to be considered for European structures. But we see with more recent standard that it acknowledges that the fact that maybe we were a little bit too conservative with the initial version of Eurocode 8. If we look now at the Indian standard, we still have something similar in the same logic with the ratio between the acceleration and the gravity acceleration. We also have a zone factor here, and we have a reduction factor R. We also have something very important, which is the importance factors. This is something pretty advanced, considering that the standard is pretty old. Because this has something to do with the performance-based design, and we'll come back to that later on during this webinar. But we can see that more or less it's the same logic. We have the seismic acceleration with some reduction factors, and actually from our experience, since we have to respect this condition as well, being always higher than the zone factor divided by 2, we almost always end in this category. And this would be equivalent to having like a 50% reduction of the initial seismic acceleration. So it's somehow similar to Planck with 0.6. Here we have something like a half of the acceleration. So once we have the seismic coefficient KH, we can use it to get the rotation of our system, the equivalent rotation, and then we can go to calculating the earth pressure coefficients, the active earth pressure and the passive earth pressure. So these are the Mononobe Okabe formulas used mainly for pseudostatic design. There are other theories more recent like Lancelota, Milonakis, but still these are the main, the Mononobe Okabe one is the main one used. The assumptions of this method are that the soil should be dry and cohesionless. The condition about the soil being dry can be overcome because we can calculate also the seismic coefficient for water, for soil underwater. And also second condition is that the movement of the wall should be sufficient to fully mobilize the shear resistance along the active or passive failure surface. And most importantly, the acceleration that we consider for this model is uniform across the retaining wall, which is also not very realistic because we have always varying acceleration that increases when we are going up. So if you move now to the dynamic method, this method uses finite element software like Plaxis, Flag, Abacus. We also have some open source software like OpenSeas and LSDyna. This kind of design requires high level of knowledge and geotechnical understanding of the structure and the soil. But we believe that with the software, we see that the software are becoming more and more user-friendly, and also there are more and more available correlations from literature that are simplifying, also finding these numerical parameters that are needed. If you have a good understanding of soil behavior, you can achieve realistic modeling of the structure, and then the result would be a reliable use of this method in a simple and quick way, even for pre-design, to having quick results before going to detailed design. So if you want to look now at the specifics of dynamic design, one very important aspect is the soil constitutive model that you will be considering for your design. This is even more important for dynamic calculations because you need to account for the nonlinear behavior of the soil. The more most known constitutive models are hardening soil, small strain, sunny sand, PM4 sand, PM4 silt. There are many and many also being developed by researchers. The one we use when we are doing a Plaxis design is mostly HSS small. We believe that this is a constitutive model that gives a good compromise between the accuracy of results and the complexity of parameters. We find that it's a constitutive model that is suitable for industrial use. We see here the parameters needed for hardening soil, small strain. The first two parameters are just the weight of the soil, so easily available. Then we have three stiffness parameters that are also easily available by odometric tests. For example, we have here a numerical parameter that is taken, from my knowledge, only two values, either 0.5 or 1, depending on the soil. Friction angle and cohesion also very easily available and very important ones actually. Also, we have the Poisson ratio, and then we have these two parameters, the shear stiffness and also the strain at 70% of the shear stiffness. These are the most complex ones. These two parameters help us to define this reduction curve. We need to redefine this curve because we have the reduction of stiffness that needs to be accounted for when we have higher strain. So this model accounts for strong stiffness variation with increasing shear strain amplitudes, especially in the domain of small strains. And also we have the hysteretic nonlinear elastic stress strain relationship, which is also applicable in the range of small strain. If we take other soil models, for example, like sunny sand, it needs something like 20 numerical parameters. Most of these parameters are not well known and needs full calculations to calibrate the model and to get them. And that's why we believe even if they will certainly give more reliable results, they need much time and information that is sometimes not available for industrial use, for design offices that need to get quick results and reliable results. So the only problem for this soil model is that it does not yield reliable results if we have significant excess pore water pressure. For example, in loose sandy soils subjected to strong earthquake motions. Another aspect that is very important is the geometry of the model and the mesh. So generally, we would like to have the boundaries far enough from the model to not interact with the model itself. So general recommendation is to have a model that is 5 times larger than the height of the model. And then concerning the mesh size, we also have some conditions to respect. The first one is that simply the mesh elements should be small. They should be small relative to wavelength. So if this is your wave and these are your mesh elements, the mesh size should be rather small relative to the wavelength. It will depend on the mode that you are using. If you are using a 6-noded mode, you would need mesh elements 10 times smaller, and if it's 15-noded, the recommendation is to have it 5 times smaller. Here I'm giving just a practical tip for having this condition. You can just look for the lowest expected wavelength and have your element 10 times smaller than that exact wavelength. The second condition, is that the fastest shear wave should not travel more than one element during one substep. So if you look at the scheme here, if your wave is traveling this small distance here during one substep, it should not be larger than the mesh element, because otherwise your element here would completely miss the wave going through it, and we don't want that to be happening. So we end up with an interval for our mesh size. It should be higher than this distance and lower than the wavelength. Another aspect is the boundary conditions, because if you just use your model, not caring about the boundary conditions, what would happen is that the waves would reflect at the boundaries actually, and in reality waves do not reflect, they go to infinity. So we need some kind of absorbent boundaries that reflect this reality. In practice, what we use in Plaxis and the best boundary conditions are tight degrees of freedom. This can be used in 1D models especially, but also in 2D models, especially if you have a symmetrical model. If you don't have a symmetrical model, for example, if you stop the model here in the middle and you have the excavation level here and the ground level here, you will not have the same nodes at the right boundary and the left boundary, and then it's advised to use free field conditions. For the bottom boundary condition, we use compliant base, which is simply a boundary condition that allows absorbing the waves that are coming from the top, that are reflected at the top and are coming back down. They need to be absorbed, and also allows us to introduce the ground motion. Next slide, please. Yes, thank you. I'd like just to go back to the ground motions. Yes. So concerning the ground motions that we will be using at the bottom of our model, they need to respect some conditions. I'm just waiting here for the slide to come back. The ground motions. Okay, sorry. So as I was saying, the ground motions need to respect some conditions. So we need to be aware that the outcropping motion is usually having an upward wave and a downward wave. So that's double the amplitude that we will be having at the bottom of our model, that will only be having the upward wave. And that's why we need to consider a factor of 0.5 when we are using the ground motion. Sorry, I'm just getting aware that this is not the right slide. The one about the ground motions, please. Yes, thank you. So as I was saying, the outcrop motion here has an upward wave and a downward wave. So it would have double the amplitude that the motion that we are introducing at the bottom of our model, where we only have upward wave, going through the model. So that's why we need a value of 0.5 for the dynamic multiplier. Also, the ground motions that we are used, they can be artificial or based on real earthquakes, but they need to be fitted to a certain spectrum. And this is what we see here. This work was done by Professor Gazetas, and we see here the blue motion that was recorded from the L'Aquila earthquake in Italy in 2009. And we see in red the fitted motion, or the artificially modified motion, in order to fit with the Eurocode 8 spectrum. So we can also have a look at the spectrum now, the initial one that was far from the spectrum, and the second one that is fitting exactly with the envelope of the Eurocode 8. So this is also some conditions that are given on the ground motions that needs to be considered. So once the ground motion is fitted to a certain spectrum, we can use it also for the PGA that we have for our project, simply by scaling the signal to the required PGA. Next slide, please. Okay, another aspect is the hydrodynamic loads. And for that, we need to consider special aspects. We can either model the hydrodynamic loads by added masses approach. And for that, we simply attach certain masses to the plates that are modeled in our sheet piles. And that way, the hydrodynamic effects will be simulated by the inertia forces associated with these masses. In practice, what we do in Plex is we have different plates in the length of the sheet pile, and we simply change the mass, so the weight of the plate, not touching the stiffness parameters of the plate. We can also use acoustic elements to simulate the water, but this is unfortunately not available in Plaxis and can be used, for example, with the Abacus software. From what we've seen in the previous studies is that the effects of hydrodynamic loads, when modeled right, should not exceed 5 to 10% and should not have an effect on the bending moments of more than 5 to 10%. And this is what we sometimes see. We've seen it before with certain projects. When we are modeling the Vestergaard load as a static load on the dynamic phase, we end up with an overestimation of the bending moments, and this is not correct. So moving now to the next slide, please. Yes, I would like to end with some practical tips about the dynamic design. So just to end this part about dynamic design, it is advised to use a mirrored geometry to examine the effect of the ground motion on both directions in only one calculation, so that we can also save time. Also, it is advised to use 6 noded elements instead of 15 noded elements to save time. And also the undrained A mode is advised in these cases. We can also use dummy lines, as you see here, near the boundaries in order to have proper alignments for the boundary conditions, and so we can be able to use the tight degrees of freedom boundary condition. So now I would like to present an animation about what's happening during an earthquake when we are doing a finite element design in Plaxis. Let's see the animation, please. So I would just like you to pay attention to the whole soil body moving. So of course, this is exaggerated. I think it's scaled up 20 times, but this is in order to see what's happening during the earthquake. What's important, as I said, to mention is that in a given second, the soil body will all be moving, for example, over 20 centimeters. So it's not reasonable. So it's not reasonable, for example, to ask as a condition of deformation that the sheet piles respect this particular this deformation limit, for example, of 20 centimeters if the whole soil body is moving by more than that. So that's why it's important to see what's really happening, and to also something that we'll come back to in the performance-based design, to consider really what is important for the structure, and when defining the deformation limit, to keep this in mind. So now I'll move to some comparative studies that were done previously in the recent years, starting by the study from Professor Gazetas, where he investigated the seismic response of sheet pile retaining walls. Using the given geometry here, he considered dynamic calculations using both Abacus and Plaxis software, and also comparing them to pseudostatic calculations using Rideau. For his design, he considered 3 outcrop motions for each level of earthquake. So at the end, he has 9 motions, and we have different soil conditions as well. So the results that we had from this study comparing pseudostatic to dynamic is, as you can see in the bending moments. Next slide, please. Yes, thank you. So you can see here for an acceleration of 0.15 g, for example, if you're looking at the Abacus line and the Plaxis line, they're perfectly matching in terms of bending moments at 1600. If you look at the subgrade reaction model here in Rideau, using the pseudostatic method, we have something like 2400. So that's already an increase of about 50% in bending moments only for an acceleration of 0.15 g. If you look at the second case of 0.30 g, we have a further increase in bending moments and overestimation of about 60 to 70%. If you look at the last case here of 0.50 g, you can maybe think that it's closer to the bending moments of the Plaxis and Abacus, but in reality, we could not do the calculation for 0.5 g because the pseudostatic calculation was only limited at 0.4, and we could not do anything for 0.5 using the Mononobe Okabe formula. So looking now at the deformations, next slide, please. If you look at the displacements, it's a bit different than what we had for bending moments. And we could see here, for example, for the first case, in Plaxis, we have a lower displacement than in Abacus, and the pseudostatic calculation matches rather well with the deformations for this case. In the second case, however, it goes a little bit over the calculations from finite element modeling, and Plaxis are Abacus, and Abacus are matching quite well. For 0.5 g here, again, this is only for 0.4 in pseudostatic, so we do not have the results for 0.5, but we see that there is a big difference here between Plaxis and Abacus, and this might be due to some anchor failure in this particular Plaxis calculation that led to this shape of the sheet pile moving too much. But this also can come from the soil constitutive models that were used and the differences that can exist between the two finite element software. Moving now to the next study and the most recent study. Next slide, please. Yes, thank you. So in this study with our consultants from our partner consultant from Spain, Sener, they also compared seismic performance of sheet piles using pseudostatic method and the dynamic method. In this study, we wanted to cover a wide range of geometries. So we considered 4 different water depths for our cases. And the total cases were 11, subdivided in 3 categories. So for the first category, we had 2 water depths with a low seismic acceleration. And the second case, we had 4 water depths with rather high seismic accelerations. And in the third one, we wanted really to push to the limit, considering high seismic acceleration, very high seismic acceleration actually in soft soil conditions, to really go to the limit of the methods. Moving to the next slide. Next slide, please. So here we can see the results for case 2.1. You can already have a look at the bending moments here, and you can see that the pseudostatic method overestimates in a big way the bending moments up to 92% here for this case. If you look here also at the bottom of the sheet piles, you can already guess the difference in length between the dynamic method in the blue line and the pseudostatic one in the orange line. And so this effect, combined effect of bending moment reduction and sheet pile length reduction, of course, has as a result a big saving in tonnage. So in this particular case, we can achieve a saving of up to 48% in tonnage of sheet piles, which is of course huge, considering that we only changed the design method and nothing else. Moving to the next slide now, with the results from case 2.2. Next slide, please. So looking at the, thank you. Looking at the results now from case 2.2, we see that we have a similar effect in bending moments with the big increase in bending moments when considering pseudostatic calculations. So in this case, up to 59%. And also combining this with the reduction in length, we end up in huge savings in tonnage as well. If you look now at the extreme case 3, with high seismic acceleration in soft soil conditions, you only have one figure here, one line, which is the one from Plaxis dynamic calculations, because we don't have any results using pseudostatic calculation again, which is very problematic because we became aware that in certain seismic areas, you can simply not design sheet pile sections if you rely on these conventional methods. So moving now to a very important topic, which is performance-based design when talking about seismic calculations. So this is a rational approach to the design of structures that often yields in very good results when compared to conventional design methods. In this approach, the consultant design engineer works together with the owner to identify specific structural performance objectives for serviceability and also for strength. Then the structure is designed to ensure compliance with these agreed objectives. And in practice, what this means is that we define a certain grade for our structure. If you look at the graph here from Pionk, you have 4 different grades. So if, for example, defining a grade S, which is the most important one, or meaning that structure is very important, we also need to define 2 levels of earthquakes, level 1 and level 2. Usually the level 1 will be the 72 years return period earthquake, and level 2 would be something like the 475 years return period. And once we define the grade and the earthquake levels, we also define the performance criteria and the level of damage expected for this given structure for each earthquake. So for example, if we define, we decide that our key wall will be grade S. So that means that for a level 2 earthquake that was already defined, for example, 0.5 G PGA, we will not be accepting anything more than repairable damage for this earthquake. Of course, you need to be aware that this comes with a cost. So the project owner needs to be aware that if he's asking for this grade, he needs to have maybe a heavy structure, a heavy solution. So he needs to decide based on what the key wall is meant for, on the grade of the structure, and also on the criteria, performance criteria associated with this grade. A practical example is the 3 ports that were designed in the west coast of the US, the port of Los Angeles, of Long Beach, and the port of Alaska. They have all 3 been designed according to the performance-based design. So there were 3 levels of earthquake actually defined for this design. The first one was the 72 years return period earthquake. The second one was the 475 years return period, and the third one was a very extreme one with 2,470 year return period. And once we define these levels of earthquake, we define also the performance criteria that is associated with these earthquakes. So for the operating level earthquake, the performance criteria was that no interruption to operations shall occur, and also no significant structural damage. And all the damage should be aesthetical and located where it can be observable and repairable very quickly. So we want that for this rather low earthquake, no major damage is happening and very quickly repairable. For the second level of earthquake, the performance criteria that was determined is a brief and temporary loss of functionality, and that all functions should be restored within a few months. But we also accept permanent deformations, but in a controlled way. So it's also important to keep that in mind. Deformations don't mean that the structure is fallen or that there is some kind of failure. If it's controlled damage, then it can be okay for the structure if we know what performance we are really aiming at. For the port of Alaska, they also had some what they call seismic bursts, which is a specific berth that was designed to be more resistant than the other bursts. And for a level 2, so a contingency level earthquake, it had the same criteria as a level 1. So we really wanted this particular berth, to be very resistant in order to, for example, if we have a high earthquake, to be able to use at least this one for emergency, for maybe repairing works as well. So this was the idea behind that. For the third level of earthquake, of course, we only expect life safety and collapse prevention. We cannot expect anything more with the very high earthquake. We have to be reasonable. Otherwise, the structure would be also very costly. So also, when talking about performance-based design, we also have to talk about the damage criteria. So it's we need to have this performance criteria also based on the damage criteria. So looking at the Japanese standard, if we are looking at structures with no repairs needed, the deformation limitations are 30 centimeters for shallow structures and 50 centimeters for deep structures. But more importantly, we need to be careful to the differential displacements, and the limit here that is defined is 30 centimeters. And as it was said before and shown in the animation, it's only reasonable to look at the differential displacements and not the maximum deformation of the sheet pile, because if the whole soil body is moving, it's not reasonable to look only at an absolute value. If we look now at the working group 34 of Pyongyang, again, we have a criteria that is given by a percentage of the height of the wall and also on tilting of the sheet piles. But again, we find this differential horizontal displacements that needs to be respected, which is 30 centimeters. So moving now to some water-related issues, just saying a few words about these issues, starting with liquefaction. Next slide, please. Yes, thank you. Okay. So just let me get to the right slide. Yes, thank you. So just saying a few words about liquefaction, just a reminder of what liquefaction is. So we know that when saturated cohesionless soils densify under cyclic loading, we generate excess pore water pressure, and then the effective stresses tend to decrease. And if they reach the 0 value, then the soil will move from a solid state to somehow a liquefied state. This liquefaction for anchored sheet pile solutions can occur either in this area here near the anchor wall, and in this case we'll have this kind of failure. It can also occur behind the main wall, and that would increase significantly the active pressures, and then also would end in a failure like this, maybe an anchor failure. Also, it can occur at the bottom of the sheet pile. In this case, we have a decrease in passive resistance, and we have this kind of failure. Anyways, if we have liquefaction in our structure, that means that design was not done properly. Because what we can do against liquefaction, of course, we can model it and try to understand it, but the most important thing is to avoid it, because if it happens, it's not good for our structure. So what can be done is just try to evaluate the probability and susceptibility of our soils to liquefy. There are many methods that are presented in the standards. We even find in Eurocode 8, for example, some methods based on in-situ testing, such as SPT and CPT. They can be used to assess the probability of liquefaction. And if we see that our soil is a liquefiable soil, then we don't have a choice but to improve it or replace it. So moving here to an example of an experiment that was done on dikes. Next slide, please. Yes, thank you. So in this particular example, we wanted to see the effect of tsunami, so overflow on a dike. On the left side, you see a dike that is at the 0 second, so a normal state, and then we have an overflow. And then after 28 seconds after the earthquake is gone, so the dike is completely swept. This can be due to two effects. So first, the seepage below the dike, and also there could be some kind of liquefaction that causes the dike to completely fail and to be swept. At the right side, we have a double sheet pile wall installed inside the core of the dike. And we can see here that after the same period of time, of course, we have here water scouring, the soil is going here, but the height of the dike is kept. And we can see also that from this side, nothing really is happening. And this can be explained by two things. The sheet pile is keeping the seepage from going below the breakwater, and also, and it's a subject of many research now, the sheet pile double walls can also be used as a mitigation against liquefaction. We will see here now a very realistic and in reality example of this in the tsunami that happened in the Kamaishishi in the region of Iwate in Japan. This tsunami happened after a 9.1 magnitude earthquake, and we can see here an aerial image before and after the tsunami. So here, if you look closely, there is a double sheet pile wall that was installed for the flood gate that was being here constructed. So there was a flood control gate being installed. That's what you also see here after the tsunami. And after the tsunami, unfortunately, the houses are completely gone. But we can see here that the double sheet pile wall is still here, and also the gate is still here. We can see it also in the next slide now. What we can see also is the concrete wall that was used to protect the city that is completely gone. And we can also see now the huge size of these concrete elements. That was not enough. Also proves that it's not only about size, but also you need to understand what's happening. And here probably some effects also of seepage and liquefaction were involved. If we look now again at the sheet pile wall, and also we have this picture here of the double sheet pile wall at the left protecting the flood control gate, and the right, again, unfortunately, the houses are completely gone. But if you look also closely here, you have the concrete wall that was damaged, and we have some sandbags that needed to be used in order to temporarily repair the wall. So if you want to try to understand what's happened here, we can look at another picture now of the sheet piles closely. So we can also see here that, again, with a close picture, no damage occurred on the sheet pile wall. And we can say that it's completely protected the cofferdam from liquefaction. As I said before, there are many researchers now looking at this topic of double sheet pile walls mitigation effects against liquefaction, because it is believed that the soil that is trapped here between the two sheet piles is somehow separated from the soil that is shaking, and also we cut off the excessive pore water pressure and it can be a very effective mitigation against liquefaction. So I would like to end this webinar by presenting some of the publications that are foreseen for the next future by ourselves. So first, the Seismic Sheet Pile Handbook. Previous slide, please. So this document will be published very soon, and it has the general recommendations on seismic designs of sheet piles. It was drafted in collaboration with the University of Cambridge, University of Rome, also based on the results of our studies with CENER, with Professor Gazetas as well. It also includes a step-by-step tutorial with a work example in Plaxis, and gives further detailed instructions on design and recommendations. This, as I said, will be published soon, so if you're interested, do not hesitate to get in touch with us to get a copy as soon as it's published. Also, the Seismic Design Brochure, this 4 pages document that condenses the results of the CENER studies that were done. In this webinar, I only mentioned the results of the last study, which was about comparing dynamic and pseudostatic, but we also had previous studies about hydrodynamic loads and also about general methodology of sheet pile design. And in this brochure, you can find also some elements about the previous studies with CENER. To conclude this webinar, I would like just to say again that the conventional Mononobe Okabe approach using pseudostatic design is not suitable for sheet pile solutions, especially for high seismic areas. And we've proven it, and we've seen it now, and it's simply related to the formula itself. We advise to use dynamic methods using finite element software to allow for more realistic modeling of the soil, also taking into account the non-linearity of the soil and all the aspects that were previously mentioned. However, this, of course, needs to know-how and some kind of knowledge about geotechnical and structural engineering, also knowing the parameters and how they influence the design. We've also seen that sheet piles can be used as protection measures in cases of tsunami, for example, and liquefaction. All in all, I would say that if you are using accurate FE finite element studies, this will allow significant savings and can even yield for economical sheet pile solutions in some areas where we cannot even achieve a solution using pseudostatic design. Also, if we combine this with the performance-based design approach that accounts for controlled damage, that would even increase the savings and make it even accessible for sheet piles to a wider market range. So if I want to summarize the main message today is that if we are using advanced design methods again in an efficient way, we're sure that we'll yield in economical sheet pile solutions in high seismic areas. So thank you for your attention, and I'm available for your questions now. And thanks again.
Thank you, Mr. Ramin. It was a wonderful presentation. Now, we thank ArcelorMittal, the webinar series sponsor for the steel retaining structures and foundation webinar series. We thank the other webinars, Kamar Infrastructure Private Limited from Mumbai and Teamwork Engineering Solutions Private Limited from Chennai for sponsoring this webinar 2 session. So before moving to the question and answer session, we will watch the promotional video from our sponsors.
My origin is somewhere in the depths of the earth, and my story began billions of years ago. when I was born in a blaze of fire. I helped you survive through the ages. I've changed the way you work. And I've changed the way you live. I've been part of mankind's greatest achievements. I allowed you to expand your frontiers, to explore the land, the water, the skies, and even the universe. Throughout the centuries, I was reborn again and again. I'm known for stability and strength. My quantity is measured in millions of tons, but my quality is defined in millions of an inch. I've stretched the possibilities of human imagination. I've inspired you to shape your visions and reach new heights. Once I'm back to where I came from, I can become virtually anything you can imagine. I am more versatile than I have ever been before. I'm always with you. I'll protect you and guide you. I'm all around the globe, wherever you go. I'm everywhere and will always be. I am the engine of innovation. I am the pulse of the modern world. And you'll build your future on me, because I am steel, the fabric of life.
Infrastructure is a leading name in sheet piling contractor, one of the fast-growing company in the field of foundations work such as sheet piling and liner driving. Infrastructure's vision is to serve our customers better than the expectations. Our principles of the simplicity of design, reliability of performance and durability for exceptionally long service life continue to be central to our business. Have the construction experience and the technical ability to help customers find reasonable solutions to challenging projects such as
Larsen & Toubro Limited Mumbai Coastal Project, Larsen & Toubro Limited, Ishwar Gupta Setu Kalyani, Shapur Ji Palonji, KWIC Salab, Larsen & Toubro Limited, WDFC Pardi, JMC, HDFC, Kolkata, Afghans Infrastructure, Annaram, Telangana, Swastik Bridge and Road Contractor Pamban Bridge, Tamil Nadu, Tata Projects, MTHL, Belapur.
We firmly believe that customer is our assets.
Now I sessions.
Okay. Thank you very much, DFI, for giving us this opportunity, and thank you, Amin, for that wonderful presentation. We have a couple of questions from our listeners. I'll take the first one. This is from Mr. Upkar Raut. He's from Bolin Group, India. So I'll just read out the question for you. So as he asks, as shown in the animation, apart from the sheet piles, the tie rod and the connections are also critical. Are there any additional measures to be taken in consideration of the tie rods also? If so, what are those considerations?
Okay, so if I understand right, the question is about what measures can be done to secure the tie rods also during an earthquake. For tie rods, what is the main problem that can happen is, for example, if we have a very high active pressure due to the earthquake on the wall. So if we have very high active pressure on the wall, of course we have additional loads on the anchors or the tie rods, and this needs to be also designed. So when we are do this, what I presented is the geotechnical design mainly, but also there are some verifications, of course, on the steel stresses on the anchors, also on the sheet piles. So of course, in this dynamic calculation, we'll get the actual forces and loads on the tie rods, and these high forces needs also to be accounted for the verification. So this is what I see from, if I understand right the question, we need to do the steel verifications for the anchors based on the forces that we get also from the dynamic calculation. I hope that answers the question.
Yeah, I really hope that answers Ukkar's question. So if it is not, then Ukkar, you can call one of us and we'll be able to give you a detailed response. Okay. So the next question is from Mr. Anil Kumar SV. So this is an interesting question. He says, as the subgrade reaction model is predicting a higher bending moment compared to FEM or finite element method for dynamic calculation. So is it the same with static analysis also? Does it give the same results if you're doing a static analysis instead of a dynamic analysis? What is our experience on that?
Well, the topic of today's presentation is the seismic, but for static, Plaxis is also a good exercise. Finite element modeling is always a good exercise to control what we are doing with simple models or simple methods like the subgrade reaction models. As we did before, when we only had the limit equilibrium method and then we had the more advanced subgrade reaction model, we could confirm the models from limit equilibrium. And now what we do is that with finite element modeling, sometimes when we have a complex situation, underground car parks with different load cases, we also have first a redo, for example, the software subgrade reaction model redo model, and then we compare it to Plaxis. And in reality, if the models are done correctly, we end up with pretty much the same results. Maybe we can optimize more on Plaxis side because we have more realistic modeling of the soil and the behavior. But the critique that we have is mostly for the seismic calculation and this Mononobe Okabe formulation. I hope that answers the question.
Okay. Maybe we can try it on static analysis and see how it works out. Okay, another question is from Mr. Rajan Peter. Have you done any studies on the behavior of sheet piles in earthquake areas, actual projects, experiences, is what he's asking.
Well, it's a complicated task to do that. So in practical terms, that means that you design a port or a key wall, and you have to monitor it and wait for the earthquake to happen to see if this matches the reality, the design. It's not possible to do. I don't believe it's possible to what we can see is we see the damage after the earthquake, and then we go around, go back and see the design. This is what researchers do in order to develop new methods and constitutive models. There are many examples. The most famous one that is always used in this particular example is the Kobe earthquake, and this was actually one of the biggest earthquakes that also shed a light on the liquefaction problem. And based on this earthquake and what happened and the damage description that was after the earthquake, people developed models afterwards. But we cannot say today that we are designing a key wall, a sheet pile retaining wall, and then we also test in reality if it's happened, because we do not control nature, and then it seems rather complicated to do.
Okay, but we can check some of our archives, and if we find any studies that are pertinent, we can always mail it to you through DFI. We'll check on that.
Yes, of course.
So the next, how do the Winkler spring-based methods fare against the Mononobe Okabe method? This question is from Mr. R. Ramon Varghese.
Sorry, can you repeat the question, please?
How do the Winkler spring-based methods fare against the Mononobe Okabe method?
I don't have experience with the Winkler spring methods. I think that for industrial use and for geotechnical modelization, what is mainly used is the subgrade reaction models. But I cannot comment on Winkler method, because from my experience and from my knowledge, this is more for academical uses and for research purposes. And this requires a lot of calculation, a lot of numerical calculation that is maybe in our case not valid and not available for design offices. So I cannot really comment on that, but I can also have a look and come back to you later on that topic.
Okay, we can respond. In any case, we are going to respond to all these questions through DFI. So we will probably include that bit of explanation for this particular question as well.
Yes.
Thank you. I'll take the next question. The next question is from Mr. P.S. Sen Gupta. So in case the soil behind the sheet pile is soft clay, whether drained or undrained parameters have to be considered. So is soil hardening applicable for such soft clay soil?
Can you repeat the question, please?
In case the soil behind the sheet pile is soft clay,
yes,
whether drained or undrained parameters have to be considered. Is soil hardening applicable for such soft clay soil?
Well, first, for clay soil, and more so than for example, sandy soils, we would be needing to use undrained models. Whether if hardening soil small strain is adapted or not, I think that for this kind of soils, like clay soils, some other constitutive models might be more adapted, like PM for silt, or I believe there are also other constitutive models really for clay itself. And I believe that they will be more adapted than using hardening soil, which is more for granular soil and more adapted for this application.
Okay.
Also, sorry, if I could just comment on the previous question about the Winkler models. This is also already included in redope or the elastoplastic models, because elastoplastic models use springs. And so I don't know if there is a specific method, seismic method, only on Winkler and has nothing to do with Mononobe Okabe. I don't believe so, but it's already included in the subgrade reaction models by the Mononobe Okabe formula. So I think that the question does not exist, because both might be the same calculations.
Okay. Like now there is a question, it is a general question, not perhaps completely related to seismic, but I'll take that in any case. So it's a question from Mr. Anurag Kapoor. How much corrosion allowance should be considered for sheet piles So I am assuming it is a corrosion allowance for sheet piles, general case, and if there would be any additional corrosion allowance, if it is a seismic case, also to be considered. So you can probably answer.
Okay. Well, as you correctly said, this is not really related to seismic. There is no additional corrosion due to seismic. Corrosion values depend also on if there is a soil in contact with sheet pile, if it's water, if it's atmospheric, just air, if it's near sea areas. So there are some tables giving corrosion values. For example, for 50 years lifetime, if you have just soil behind and water in front, that would usually be 0.60 millimeters behind the wall and maybe 1.75 millimeters in front. But you can find the exact values on the tables, for example, tables 4.1 and 4.2 in Eurocode 3. But to comment on the seismic, there is no additional corrosion due to seismic. Seismic event is a brief event that happens, so there is no additional corrosion. We have to see the damage after the earthquake, but it will not be related to corrosion.
Okay. So there is a question. This is an interesting question. It is from Ms. Stefani. She asked, could you please comment on the use of water injection to advance sheet pile driving? I think it is jetting assisted driving that she's mentioning in stubborn soil, and the likelihood of inducing liquefaction problems. Liquefaction?
Okay. So the question is about use of so water injections to simplify or to have a simpler installation of sheet piles, and if this can maybe imply some also impact on liquefaction. I think it's a very interesting question, and it needs to be considered if you have this driving assistance. Maybe you need also to consider this aspect when you are doing the study of probability of liquefiable soil. So maybe it needs also to be accounted for previously in the susceptibility of liquefaction of soil. But it's not something, maybe something that is project specific and can be maybe looked at specifically for each project. But it's not a general topic that we would usually check.
Okay. Yeah, there's another question from Mr. Bishwajit Paul. So he asked, are there any limitations of seismic design in Plaxis?
Are there any limitations? No, there are no limitations. If you know what you're doing, for me, of course, there are the software limitations. But for dynamic calculations, if you're controlling the parameters, you know your constitutive model, you know what you're doing, and you can check the parameters at the end and the output, then there shouldn't be any problem with the model. But the more you know about the topic, the more reliable results you can get out of it. But if, of course, you are just using simple correlations, you have no detailed information about the soil, you have no control of the reduction curves, for example, of stiffness. If you do not control that, you have in fact and effectively this nonlinear behavior of the soil at the end of after the calculation, then maybe you are not exactly knowing if the results are reliable. But just like that, if there are any limitations, apart from the limitation of the software, I don't have anything in mind. But maybe again, I can come back to this question later, and we have a more detailed answer to that.
Okay, I think we have a question for time for one last question. So this question is from Mr. Anurag Kapoor. He's asking, would like to know if you have any suggestion for safeguarding normal concrete piles from failure during earthquake-induced liquefaction. And I am presuming from his question that what is the optimum length of these sheet piles? So maybe is there a mechanism to use sheet piles to protect the concrete piles of a particular foundation? Or if that is the case, what would be the optimum length of such sheet piles?
Actually, there are some research works on this exact topic. The most advanced method that we've seen in also in the recent geotechnical conferences is the double sheet pile wall against liquefaction. If only sheet piles can one single sheet pile wall can protect against liquefaction, I don't believe so. But of course, you can also use the double sheet pile wall. But again, this is ongoing research works and needs also more detailed analysis of the situation. About the length of the sheet piles, that would depend on the project, on the soil, on so many things. You cannot just give just a length like this without knowing really what the project is about.
Yeah, so it has to be project specific in that case. I don't have time for more questions, but we will get all these questions from DFI and we'll make sure that the answers are sent across from us, and all the balanced questions, unanswered questions will be answered from our side and will be circulated through DFI. Thank you.
Thank you.
Well, that was an excellent question answer session. I thank Mr. Amin and Amrita for responding to every single question. I wish to remind the audience that please put your name and the designation of the organization you represent. It'll help us read out in a proper way. And you can continue to put your questions in the question box, and this can be answered, be forwarded to the speaker, and you will get the answers even if it's not answered here. So I just have one small observation which I want to share with you all, especially with Mr. Amin, is in India we don't find much of steel sheet piling in the urban areas. Most of the sheet piling are in the temporary structures. We don't see much of permanent structures in our along the rivers or along the shores, and most of the sheet piles are used only. We see them mostly used in temporary structures. So this is just an observation. I hope the situation will change with the presence of companies like you, and we would welcome more sessions like this. And especially Seismic is Indian. More than 60% of Indian geography is seismically active. So we require a good design, seismic design for steel sheet piles. So after this, once again, thank you, Mr. Amin and Ms. Amrita, for the wonderful session. And we move on to the next. I wish to announce that out of the series of webinars on steel sheet piling and steel piling, the next one is on 26th. You can see in the chat box, you can see the link, and you have the brochures in the handouts. Please make a note of the date, 26th August, 4 p.m., same time as today, and it is on HC and AZ steel wall solutions for port constructions. So again, by an expert from ArcelorMittal. Please make a note of this and go ahead and register, please. Thank you. Next slide, please. So we also wish to welcome you to the DFI India 2020 virtual conference. This is a whole 2-day. It was supposed to be a 2-day full conference face-to-face. Unfortunately, due to COVID, we made it into a virtual conference. It is spread over 2 days, 19th and 20th of November, but it's a virtual conference. Please go ahead and register. The registration link is also in the chat box now. You can copy it from this also, can download the brochure. This will be a wonderful conference which will cover the whole gamut of foundation engineering. We have expert speakers and we have a big review on the pre-conference here right now. Please go ahead and register in large numbers. So as a run-up to the main conference in November, we have 3 pre-conference webinars. These are all part of the main conference in November. And once you register for the main conference, your attendance to the three pre-conference webinars are guaranteed. The first one is on 20th of August. It's not too far away. It's just 8 days away. And it's again, and the next one is in September, and the next one is in October, followed by the main conference. Please make a note of the dates and the times so that you can be present in the conference virtually. Next slide. So a word about the next conference, which is on the 20th of August at 4 p.m. Indian Standard Time. We have an excellent speaker, Dr. Amy Serrato, who specializes in seismic design of helical screw piles. So the topic is dynamic and cyclic applications to grouped helical piles. Dr. Serrato, I know her personally. Dr. Serrato is an expert in helical screw piles. She was there in Christchurch after the New Zealand earthquake, and she proved to the people living there that helical screw piles, which were foundations for many buildings, did not collapse. So she has given you first-hand information on this. She's doing an extensive research in University of Oklahoma in United States. Dr. Amy Serrato is going to be with us on the 20th. Please register yourself for this webinar. This is the first pre-conference webinar for the main conference. Please mark the date, and we request you to go ahead and register today itself. Next slide. Here you have some details of the registration for the main conference. You have individual registrations. Those who are members of DFI, Indian Geotechnical Society, have concessions, and those who are non-members and students, we have dropped the price for the students enormously. We want students to benefit for this kind of conferences. Then we have corporate registration, various groups, as you can see, and we also want to wish that these registrations are open now. It's open 24 hours across the world, and you can go and register today and pay up the fees. It's the first virtual conference, and the brochure can be downloaded from the handouts on the right side of your screen. The link is also available on your chat box. And the sponsorship opportunities are available for the main conference. We require the help of the corporates to make it through. The conference is held in conjunction with Indian Institute of Technology, Madras, and Indian Geotechnical Society. This is an annual conference with the experts across the world. One of the advantages of the virtual conference is we could get real experts to talk as keynote speakers. Please don't miss this. And we also have the offices of the DFI India standing by, and you can contact Mr. Mahendran or Mr. Atif, whose numbers and their emails are on front of you. Next slide. Now, to move on to a little bit different topic, is DFI also has other initiatives. One of the initiatives I'm going to talk about for a few seconds is the continuous flight auger technology for installation of piles. So DFI have taken this initiative, gone through the trials, done some tests, and these are pictures from the actual job, pilot project on pile test done in India. So these are quick snapshots, and we have done these piles, and we have got the documentation done. The piles have been tested, and they have tested for vertical downward pull-out as well as lateral, and we have the documents all available in our website. Please note the website in front of you. You can go ahead and look at the project, pilot test project of CFA from the website, download and learn. This is one of the initiatives recent initiatives of DFI. And lastly, I would like to thank everybody who's attended this webinar, the sponsors, the delegates, the speaker, and Ms. Amrita for the support, and see you all on the 26th in the next webinar. Bye-bye from the DFI platform. Bye-bye.